Hello again. This is Math 2233 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Vector Cross Products and Torque. And again, encouraging you to be an active learner as you watch this video. When we adjourned last time, I left you working on this problem. I hope you finished it, but if not, I'll give you a little bit of an opportunity to do so now. You know what to do. Let's see how you did. Well, these are ordered triples, and so the first thing you have to do is realize that 3 points, 3 distinct points that are not on a line is a triangle, and that will determine a plane. And so you're really talking about vectors joining these. So we're going to have to figure out what the vectors are joining these ordered triples. So one is PQ, the other is PR, and the vector PQ, PR is perpendicular to both of those. This is the cross product, and is therefore perpendicular to the plane. And so PQ is this. Now we learned this in the first section, but that is how you come up with that vector, and this is vector PR. So we can compute that by putting PQ here and PR here as components and I, J, and K across the top. Compute this determinant, and we should have gotten this. So this is minus 40. You could have written it as pointy bracket minus 40, minus 15, and 15. So this is perpendicular to the given plane. Now any non-zero scalar multiple of this, such as 8 minus 3 minus 3 dividing all the way through by 5, is also perpendicular to this, this plane. And sometimes when I ask you questions like this, I'll ask you to convert this into a unit vector. Here's another problem for you. Find the area of the triangle who has those vertices. I think those are the same points, and so what you're going to be doing is you can benefit from some of the work you've done before. Okay, you know what to do. Let's see how you did. Well, the triangle is half of the parallelogram. And we know from the previous example that this was the vector. So the area of the parallelogram is twice that of the triangle. So if we do this, it's the magnitude of these. And it's actually the absolute value of the, well, it is just the magnitude of this vector, I guess I should say. And so here you get that this is 5 times the square root of 82. There's nothing wrong with this number. There are no ugly numbers, just like there are no ugly babies. This is a fine answer. So the area of the triangle is 1/2 of that, so it's 5 over 2, the square root of 82. And again, that's a kind of problem I often will ask on tests. Okay, now it is important that you realize that when you're dealing with these fundamental unit vectors, I, J, and K, that the cross product of them, and we're using the right-hand rule here, is that I cross with J is K, and so on and so forth. You don't have to commit these to memory, but you do have to readily come up with these. Now, one of the things you can learn from this is that I cross with J was K, but J crossed with I was minus K. So I cross J does not equal J cross I. That means that cross products are not commutative, like many things that you have studied before. Okay, so it's not commutative. You can also look at this thing, and you'll get minus J, but if you regroup it in the same order, you will get this. And so what happens is the associative law does not apply either. So some things work the same way as they did in other math, and some things don't. Here's a list of formulas that are important for you to probably be able to deal with. And so we have properties dealing with distributive properties. We have properties dealing with sort of this anti-commutative property. We have properties dealing with scalar multiplication. And I'm going to focus on 5 and 6. Now 6 we're going to do later, and this is called the scalar triple product. And we will use this calculation later, but we're going to do this one, and this is called the scalar product, a scalar triple product, because you see this is a scalar because we're dotting a vector with a vector. Here you're crossing a vector with a vector, you're going to get a vector for an answer. And so there's a difference. This is a scalar, this is a vector. We will use both of these, and we're going to look at the proof of number 5 just to see what happens. Now to prove number 5, you just can plow right through it. We're going to use properties of real numbers, but we take vector A to B, pointy bracket, A1, A2, A3, B to B, pointy bracket, B1, B2, B3, and C to be this. And so we start with this side, and we write the definition of the cross product, and then we do the definition of the dot product. We get this. We do a lot of algebra and simplification and realize that this one is this side. This proof actually isn't as easy as I'm seeming to make it, because you have to do a lot of realization and a lot of algebra there. But that is property 5, and property 5 is called the triple scalar product. And this occurs when you have this, and there is a shorthand formula for this that is A dot B cross C is, now this is a regular determinant, and so this is going to be A1, A2, A3, B1, B2, B3, and C1, C2, C3, and we calculate the normal determinant of that. So you see this is the same as this expression up here, and if you work through the algebra, you realize that you do get the same numbers. Now, what's this good for? Well, the geometric significance of the scalar triple product can be seen by looking at, and this is called a parallelepiped. It's a parallelogram, but in 3 dimensions, determined by A, B, and C. So you see one side is A, another side is B, and the depth is C, and all of these are parallel. You build basically a 3-dimensional parallelogram here. The area of the base is down here. Well, we learned that the area of the base was simply the magnitude of the cross product. And if this is the angle in between here, then the height, which is the distance from here to here, is going to be magnitude of A times the cosine of theta, the absolute value of the cosine of theta, because that has to be a positive height. So the volume of the parallelogram then is the area of the base times the height. It is this, and if you think about that, that's just the dot product between this is a magnitude of A, magnitude of B cross C times the cosine of the angle in between them, and you get this. And here we are taking the absolute value because volume is always positive. So we have that formula. So the volume of the parallelepiped determined by vectors A, B, and C is the magnitude of their scalar triple product, and that means it's the absolute value of their scalar triple product. And if we use that formula and find out that the volume of a parallelepiped determined by A, B, and C is 0, then the vectors must lie in the same plane because there's no height, so they are coplanar. So here's an example. You're to use this scalar triple product to show that these 3 vectors, A, B, and C, are coplanar. You know what to do. Let's see how you did. Okay, you just use this, you put A, B, and C like that, and you compute the determinant. Make sure you can do this computation. You get 0, that means that there is no height. That means they are all coplanar. And again, that's called the other one is called the vector triple product. And later on, when we talk about Kepler's laws of planetary motion, we will use that. Here's a little math history note about the great Irish mathematician Hamilton, and he had a early version of vectors that were called quaternions, and that's probably enough math history for now. A primary application of this is the concept of torque, though, and here what you can see is a bolt, and you put a wrench on that, and you're turning the wrench this way, but you're applying your force at an angle, and so you have to think about what is the actual force that's going to be perpendicular to this to do the calculation. But what will happen is when you turn this way, you'll be driving this this bolt into the screen, and so that's kind of what's happening here. And the idea is torque. So here we go. The idea of a cross product occurs often in physics. In particular, if we consider a force acting on a rigid body, and the rigid body, and there's two rigid bodies really. The force is acting on the rigid body, which is the wrench, and the wrench is then tied to the also rigid body, which is the bolt, at a point given by the position vector r. For instance, if we tighten a bolt by applying a force in the wrench, we will produce a turning effect. The torque, and this is the Greek letter tau, relative to the origin, is defined to be the cross product of the position vector, and then the position vector is the r cross with f, and that is the tau. It's difficult to see that. And this measures the tendency of the body to rotate about the origin. The direction of the torque vector indicates the axis of rotation. According to the theorem that we had then, is that the torque is equal to the magnitude of r cross with f, and that's the absolute value of the torque, but this is going to be the magnitude, I guess, of the torque is going to be absolute value of r, absolute value of f, times the sine of theta, where theta is this angle right here. If you think about this being theta, this is 90 minus theta, but this is also theta, and so you realize that you're talking about the perpendicular component here. Observe that the only component of f that causes the rotation is the one perpendicular to r, that is f sine theta, or absolute value of f sine theta, magnitude of f times sine theta. The magnitude of the torque is equal to the area of the parallelogram determined by those two vectors. So this is kind of tying things together in a nice physics application. So suppose a bolt is tightened by applying a 40 Newton force to a 0.25 meter wrench as shown in the figure, and you see there's an angle there as well. Find the magnitude of the torque about the center of the bolt. You know what to do. Let's see how you did. Okay, we just used the formula, so the magnitude of the torque is this, which is this by our formulas, which is this, and that's approximately equal to this when you use your calculator to get the sine of 75 degrees. And if the bolt is right threaded, occasionally you'll run across things that are not right threaded, but usually they're right threaded, then the torque vector itself is this one, where that is this magnitude times the normal vector, and the normal vector is directed down into the page, because if you're going this way, you're taking the radius cross with this, and it will go into the board. You might want to think about that, because that's a good application of the right-hand rule. In closing, now more than ever, time is precious, each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all until we talk again.